Hi, Professor. Let me begin by introducing my project for you, the research on speech emotion recognition. So let's get started. First, I would like to introduce the problem and design goals of my project. And this project is a key task that combines the natural language processing and audio processing, with the wide applications in the educational feedback, customer service, and the mental health. My design goal The design goal of my project is to improve the accuracy and the robustness of the emotion recognition model by combining the preprocessed audio data with the advanced feature extractions and classification techniques. And next, let me introduce the data source used in my project. And after investigating existing studies on emotion recognitions, I selected three classical datasets that are widely used in the field of emotion recognition. Uh, in projects like the speech emotion recognition, these datasets are almost indispensable. From the two visualization graphs, you can see that after some simple pre-processing to the naming format of the audio fields, I store the field passes and their corresponding emotions labels in comprehensive data frame, and making subsequent operations more convenient. Yeah. And the second graph shows the variety of emotions categories converted by the datasets, like the angry, the disgust, the fear, the happy, the sad, and the neutral. And although the amount of the data is not particularly large, but I think it's have about six uh like 4,000 data in here, and I think it's sufficient to support the model training and the prediction. And now let's take a closer look at how I process these fields and store them in a data frame. The first graph shows the field name format of the claimed data set, and where specific keywords in the field names indicate the emotion labels, like here, the sad, the angry, disgust. And therefore, I used a dictionary to map these keywords to their corresponding emotions. Then, by following this code on here, all this code, I extract the field passes step by step. And by analyzing the naming styles of each dataset, I customize the processing code for each format. Finally, the data frames from all datasets were combined into the comprehensive data frame mentioned earlier. And in this part is data preprocessing part, and this part follows a part of knowledge learned in our course notebook and two brand new extraction features and performance a complete processing of the data in four steps. And for the first step is the resampling. Resample audio data into a floating point format to standardize the input, and this ensures a consistent sampling rate across audio fields, providing standardized input for the model. And the second step is the removing slides. Using the LibreSAR effect train library to remove the muted portions of the audio signal and keep the main content. This helps reduce the data redundancy and improve the slice of the segment signals. However, it's worth noting that if the emotion feature contains slice like the sad emotion, some information might be lost by this emotional. And the third step is the adding noise. Yeah, add small Gaussian noise to enhance the model's robustness. In fact, the CR and RMSE are more sensitive. These two features are more sensitive to noise and more personalized data processing for these features. Could potentially improve the final accuracy However, to simplify the process, I choose to add slight noise to reduce the complexity. And the final step is padding. Pad the audience signals to a fixed length to ensure that the bench processed audience data has a consistent dimension. And now we move on to the critical part, the feature extraction, and I choose three features. One of is MFCC, a feature that has been extensively used in our course. Therefore, I will focus on the two new features here. The first one is the DCR, the zero crossing rate. The DCR feature is extracted via LibreSub feature zero cross rate library, which characterize the dynamics of the signal. Fast emotions like the angry, happy typically have high DCR values, and while the disgust or the sad usually have lower values. And the advantages of this feature include its simplicity, suitability for real-time segment detection, and effectiveness in discussing fast and slow speech emotions. However, it is sensitive to background noise and only focus on zero crossing point, lacking direct perception of amplitude, amplitude information. And the second feature is RMSE, rote mean square energy. This feature is commonly used to detect the intensity of emotions. For example, angry usually has a high RMSE, while the sad has a low RMSE. Here, the LibreSub feature RMS library is used to extract the raw mean square energy, which reflect the variations in signal energy. However, RMSE is also sensitive to the ambient noise and signal distortion. Uh, Additionally, it doesn't capture spectral information about the signal, so it needs to be combined with other features, such as the DCRs we used before. Yeah. So this is the reason why we used these two features together. And by completing each other, these three features ultimately produce the feature vector with 14 features for the subsequent model training. The FCC have 12 features and one features of ZCR and one features of RMSE. And next is the data splitting and model design part. I split the training validations and test sets in a ratio of 90%, 5%, and 5%. For model design, I used the multi-layer LSTM and GRU at the core to capture the temporary dynamics and the long and short-term dependency of the audience features layer by layer. Yeah. And the classification is completely used fully connected layers. Dropout is used to prevent overfitting, and softmax is applied to output the probability distribution of 6 emotion types. And RMS Pro was chosen as the optimizer to handle sparse gradient problems in time series data rather than Atom, as RMS Pro performs more stably in high-frequency data updates. The loss function is cross entropy, suitable for multi-classification tasks, and the early stopping was sent to avoid overfitting. But during training, the process stopped around aperture 30, and even though there was still room for improvement, I did not fully understand this phenomenon, so I ultimately choose not to use the early stopping. And after adjusting the bench size and the number of apertures several times, I finalized the training process with 100 apertures and a batch size of 33. 32, sorry. After 100 apertures, the validation loss began to grow inversely and indicating that the model was overfitting on the training set. Therefore, I choose to stop the training at the right time to maintain the model's robustness. However, as shown in the slides, I still have some questions about this part and hopes to find the answers. So if you have the reason or answer about this confusion, Professor, so please give me the feedback. Thank you so much. And finally, let's look at the result of my project. Overview, the model achieved an accuracy of 82% on the training set and 78 on the validation set. During training, the training loss consistently decreases, while the validation loss shows some minor fluctuations without significant inverse growth, indicating that the model converted well over well. From the graphs, the training accuracy steadily increased, and the validation accuracy stabilized after a repeat increase in the early stage, reflecting the model's generalization ability, generalization ability. Yeah. However, the performance on the validation set was slightly weaker, suggesting mild overfitting. Meanwhile, the sustained decrease in training loss and fluctuations in validation loss further indicating that there is still room to improve generalization. Yeah, overall, the model effectively extracted the motion features and achieved high classification accuracy, demonstrating the effectiveness of combining MFCC, ACR, and RMSE features in mention recognition tasks. And this are the lessons I learned from the project, and this includes my presentation. So this is all my project, and thanks for listening.